Here's another function word problem set up. A football field has a track that goes around it with circular ends. The track must be 440 yards for one lap. It's a quarter mile. Find a function for the area of the interior of this track dependent upon the radius of the circular region. Alright, so again, we're going to concentrate on what we don't know. One thing we don't know is the straightaway here. We don't know how long that is, so we're just going to call that x. The other thing that we don't know is the radius of this circular piece. So we'll just call that r for radius. Now obviously both ends are going to have the same radius. Okay. And then we're going to work on the constraint part of the problem. We'll leave things in yards. I guess we can change them to feet, but it just makes the numbers larger. So we'll just stick with yards, and our function will end up to be something in square yards. So we're going to start off with 440 yards, and that's going to equal, well, we have these two straightaways, one on this side and one on that side, so they're both going to be x, so that would be 2x for the length of the two straightaways. Now you're not going to be running here along the goal lines or the back of the goal post. You're going to be running around the track, so the only portions of the track you're going to hit on the straightaways are this x and this x. So the other part of the problem is, how do we find the distance around these two circular regions? Well, both of them are semicircles, so if you put them together you would end up with one big circle with a radius that happens to be r. And we know how to find the circumference of a circle. The formula for that is circumference is equal to 2 pi r. Alright, so this becomes our constraint problem. Constraint part of the problem, so we'll call this constraint. It's the one piece that we have a solid measurement on, that 440 yards. Okay, the other part of this is we want to find the area of the interior region of this track. So the area of this is going to be broken up into two pieces, just kind of like the perimeter did. The area of the inside is going to be this rectangle, and the length of it is going to be x. The width of it from here to here is just the diameter of that circle. Well, the diameter of that circle is going to be 2 radiuses. So the first part is going to be the rectangle. The area is going to be 2 radiuses, a diameter, times x. In this case I went width times length. Plus, again, the area of these two end pieces becomes the area of this circle with a radius of r, and the area of a circle is pi r squared. So this would be our area equation. Now I want to create it, change it into a function based just on the radius of the circle. So I need to substitute away this x. And the best way to do that is to take the constraint, solve it for x, and plug in the answer here. So off to the side, I'm going to go solve the constraint for x. So let's see, that'll be 2x is equal to 440 minus 2 pi r. So basically I just subtracted 2 pi r on both sides and then just flip the equation around. Divide everything by 2, and we're going to get x is equal to 220 minus pi r. So wherever I see x, I can do a nice little substitution. So I'm going to get a equals 2r times this x plus pi r squared. And then do our little substitution. X is now equal to 220 minus pi r. And all we have to do now is simplify this expression. So we're going to get area as a function of r is going to be 440r, 2r times 220, minus 2 pi r squared plus pi r squared. And then finally we can simplify these two because they have like terms. And we're going to get a is equal to 440r minus pi r squared. So depending on what we choose to be the width of our field, this will give us the area of the interior of this track. Kind of nice. And then we can play around with it and maximize it and all that fun stuff, but that's later in the book.